Hola everyone, this is a quick tutorial on GeoGebra. Again, you don't have to use GeoGebra, but you'd be hard pressed to find a better program, I think. We could look at the octahedral stresses surface in 3D. There's a 3D window, there's a 2D window, and then there's an algebra window here. Everything I think is pretty easy to understand. The only tricky part that I found was that points have to start with a capital letter. So don't forget that. And then I just used regular letters instead of the Greek letters. So I'll show you how I did this. Just hide one of them here, for instance. So don't delete things that you need them. It's a parametric program. So if something requires something lower level, then deleting it would delete the offspring. Just hide things when you don't need them. So a point here, for instance, if you wanted to just put a point on there, like I would say x face, let's call it 2, is and then I would say it's the stress here. So I could say sigma xx, for instance, and the Greek letters are here. Sigma xx and the y, and then sigma xy. This is negative, so that means it's spinning clockwise, and clock is above. So that'd be sigma xy. And there it is. If you want to, you could just see it popped up there. You could change, of course, the colors of these points and the style of these points. A nice thing about the labels is that you can actually show the values of the labels here. Right-clicking on this under Object Properties, we could show the name, or the value, or the name and the value, which is super sweet. We could do the same with the Y face here. The Y face would be, let's just call it Y face 2, is going to be sigma YY. And then it would be, oh, I guess I screwed that up. This one is clockwise, so it's above. So let me, this one be counterclockwise, so it's below. So let me put that minus sigma xy. It's almost midnight here in Barcelona. Oh, I think maybe I did this right because the double negative there. Okay, so I did something right. Midpoints are super sweet in GeoGebra. You could resize these windows. It just takes a second for it to read. Midpoints are super sweet. It's under the point menu. All of these have drop downs, of course. I can say the midpoint between here and here would be that red diamond. Let's call that mid something, mid 2 or something, just so I'll find it. And then I could do the radius. I could figure out the radius of this circle, which would be half of this segment if you wanted to make a segment here. I don't remember how I did the radius, but well, I could do a segment between the center and that one of these points. So let's just draw one here, and let's call that radius 2 or something. Another sweet thing that you might use later is that the segments are defined by their lengths. So I could just refer to this radius 2 in an equation. I don't have to say length of radius 2 or anything. I could just say radius 2, and that would be 50 for us. I can hide this just to keep things uncluttered. And then I could draw, let me hide this circle here. And then I could put a circle in here. Circle with center through the point, but that would be a variable. circle with center and radius, so you can click on that, and then it's asking for the radius, and I think it was radius 2, which I just called it here. So that shows up sweetly. This was a little more complicated, of course. I drew, Control Z. Don't you wish life had a Control Z? I drew these radii, these points, I drew these lines, and then I drew a surface perpendicular to that line in 3D. And then I found where it intersected the X and Y and Z axes here. So let me just show you what I mean there. Things get a little cluttered here. So let me just show you, let me just do a line here really quick just to show you. Let me just do one just to show you what I mean here, like a parallel line for this edge here. Alright, so I just selected that. I'm going to just select that vector here and drop it here. Okay, so I just drew a line. This isn't super meaningful. I would figure out the point for tau octahedral, and it would be on that line going through the center here. That's not the point of this exercise here. What I want to do is show you if I had a point defined like sigma octahedral, which I did here, but let me just put a point on here just to show you about perpendicular plane. So we have a nice tool here, a plane. It's a perpendicular plane, so you select a point and then the perpendicular line here. So a point and then the perpendicular line. And then what I did was I just let that intersect these axes to get the lowercase a, lowercase b, and lowercase c of those oblique planes that we were talking about earlier. The intersects are really powerful here. So I can intersect this plane with that axis, for instance. And then I got that point here. Points are referred to there. I can grab the x value of a point or the y value of a point. Those are going to be lowercase letters. So for instance, if I wanted, well, let me show you how I did octahedral point here. So double clicking on this would be open up the definitions box here. So this is octahedral point, and I took the x of octa h, the x of octa h again, and the y of octa h. Now what is all that about? Well, octa h is here, which I grabbed from those cool arc radii. So let me just show you how I got those arc radii here. I don't know if I explained this in a previous video. It seems like I said this before, but maybe I didn't. Maybe I said it to some other students. So I put a point on this axis here, and it's anchored to that axis. And then I'm scribing those arcs using this circular arc command right here. And if you could just read the prompts here. So it says select the center and 2 points. So that center was that slidey point here, and then for instance B1, and I want to target here sigma 3. Remember that? I think I explained all this. Can't remember. But now obviously I missed that target, but here now if I move the slider, you could see that I could just get it right in there the way I want it. So that would be that first arc, and then I'll just leave it here so you could see it. And then I did the same with the second arc, and I just put a separate slider on here. So a separate slider, I just dropped that down here. And now I'm going to go from B3 to sigma 2. Remember that's in the steps there. So the center, and then I think you got to go this way. If you go, I'll show you what happens. If I go this way, it's going to try to go all the way around here to here. See how I made that arc all the way around? So So I want to do the circular arc center from sigma 2 to B3. That's my target. You could see the arc is lifting. It's not, I just put that point down kind of randomly on this axis here, and you could see there I missed it, and there it is again. And then I would find the intersection of those two arcs with this and this, for instance. And then that point I called octahedral H. And then when I plotted this point, this is a 2D, remember, a 2D projection of a 3D problem, really. This is this 19th century idea, which is super cool. And then, but it's 2D, so I want this in 3D, so I want the x value of that and the x value again to be in 3D at 45 degrees. It would throw me into this quadrant here, shooting out at 45 degrees. So that tau net point pulled the x value of this, the x value of this, and the y value of this to give me that point. So I'll show you here tau net point, how I did that. Oops. Oh, that's tau net, sorry, I'm looking at the octahedral point here. The octahedral point was x of that value, x of that value, and y value. Tau net point was coming from the steps in the previous videos. Tau net multiplied by the tx direction cosine, tau net multiplied by the ty direction cosine, etc., etc. All the matrix equations are done in GeoGebra here. So for instance, T transpose is, that's the T matrix, but the T transpose matrix is right there. It's transpose of T matrix. For instance, stress nu is T matrix times stress times T transpose matrix. So you could do, you can't loop in this, so it's really not appropriate for a matrix methods class where there's lots of looping. But for a problem like this, I think it can't be beat in terms of visualization. Plus you get this super nice treat, which I never noticed before, that this octahedral plane is this diamond around the more circles. I think I showed you, I'm sure I showed you this, didn't I? Gosh, I can't think. That function with the roots crossing over. This is just zooming up and down and up and down. I'm just interested in the zeros, but I don't really need the zeros. That would be approximate here. I used the cofactors approach here with A1, B1, C1, and the Q value, R value, S value. That's probably too brief of a tutorial, but you guys are good. You guys are Cal Poly graduate students. Most of you are. So I'm going to leave it at that. Like I said, you don't have to do the graphics part computationally, but I do want you to do the graphics part at least manually, because it's really nice to explore it once in a while. All right, I'm going to go to sleep.